About a month ago, I saw Matt Parker put out a video on his Stand Up Maths YouTube channel about the higher order derivatives of speed. You know, speed, acceleration, and then there's jerk, and then there's more. But at the end of his video, he put out an open question: did he experience snap? Or was it just noise in his data?
So look at this. That is a lot of snap. Okay, I mean, I know snap is all, oh snap, but that's too much snap. I think that's noise in the data. So maybe snap. Let me know in the comments below. We'll do a vote.
So, did Matt experience snap? One thing I noticed is the units are huge. I'm not sure what those units are in, but even for jerk, the units are getting big, and then for snap, the units get even bigger. It seems like snap is pretty flat, and then there's giant spikes in it. What is snap? And maybe we should go back to Matt to explain it.
What's that called? What do you call the rate of change of jerk? Well, if you change being a jerk, that's an oh snap situation. Rate of change of jerk is snap.
Okay, so we can see here Matt Parker explaining the derivatives of distance. So just your position somewhere is your distance. But if you're going between 2 points and you're moving, that's your speed measured in a distance over time, in this case meters per second. If there's a change in your speed, that's an acceleration, meters per second squared. If there's a change in your acceleration, that's called jerk, meters per second cubed. If there's a change in jerk, it's called snap, meters per second to the fourth. So these are just derivatives of the previous one.
Rate of change of snap is crackle. And after that is pop, because physicists just think they're that funny.
So there we go. There's the premise. Speed has higher order derivatives. Matt Parker went on a motorcycle ride to see if he could experience them. And then his open question at the end is, did he experience snap, or was it just noise in the data? Spoilers, yes, he experienced snap. But first, I want to do a thought experiment. So let's imagine, if you will, a car in motion coming to a stop. Get ready for this. Look at that. A car drove, came to a stop. Now, thought experiment. How much speed does this car have in this moment when it stopped? 0. If you said 0, you're right. How much acceleration does this car have? 0. Is the car experiencing any jerk right now? No. Snap? No. In fact, all the higher order derivatives of speed are going to be 0 because it stopped and there's no change to anything. However, a moment ago it was moving. Right here. Car's moving. When the car's moving, it clearly has some motion to it. It has speed. Because we know the speed is approaching 0 when it stops, we know it has some acceleration. It's a negative acceleration, but it's coming to a stop. So it had speed. The speed changed to 0. A change in speed is acceleration. But it had some acceleration, and then when it stopped, the acceleration is 0. So there must have been a change in the acceleration. What do we call a change in acceleration? We call it jerk. But if it had jerk, and then it came to a stop and has no jerk, there must have been a change to the jerk, which is snap. Let me show an article from a science website. The part I have highlighted. Consider the following. Velocity does not suddenly switch on, but instead grows from 0, so there must be some acceleration involved. Similarly, acceleration does not suddenly switch on, but instead grows from 0, so there must be some jerk involved. But the jerk does not suddenly switch on, it also grows from 0, so there must be some snap involved. But the snap does not suddenly switch on, it also grows from 0, so there must be some crackle involved. But the crackle does not suddenly switch on. It also grows from 0, so there must be some pop involved, and so on. So Matt Parker, not only did you experience snap, you also experienced crackle, pop, and even higher order derivatives of those. In fact, you experienced an infinite number of derivatives of speed. There you go. Yes, you experienced snap and beyond. Now, what it's kind of interesting, you had spikes in your data. If only there is a way to have a smoother curve, maybe a sine wave type curve. And in fact, this article talks about it. Trampoline acceleration, jerk, snap, and crackle. And in fact, there was a TV show a long time ago that dove into this.
Now, girls jumping on trampolines. God bless you.
I'm sorry, that is unnecessary. Trampoline data. Authentic trampoline data. So here, these are bounces on a trampoline. Acceleration is in blue, and jerk is in red. These are measured in gravities. In between bounces, when the trampolinist is in the middle of the air, the acceleration is -1 gravities, which makes sense. And then as they're in contact with the trampoline, the acceleration changes. So then they have positive acceleration. Actually, everything above here is positive, but the acceleration is the most strong probably when this trampoline stretched the most. It starts lifting them back into the air until they launch, and then while they're in flight, they have a force of -1 gravities applied again. But you take the derivative of that, and those are these red dots, and that is the jerk they experience, because the acceleration is, I believe it's kind of like a wave function at that point with a stretching of the trampoline. It's a smooth curve, so you take the derivative of that, you get another smooth curve. Although this one's interesting because the jerk, it's like a S. It goes up and then down and then back up. And then when you're weightless in the air, when you're not touching the trampoline, your acceleration's not changing. Down here, your acceleration's constant. So when you're in the air, the jerk is 0. So when you're airborne, there's no jerk at all. The S curve nature of it, it looks like it's positive as like when you land your jump and you're stretching the trampoline to its max point. That's when you're experiencing positive jerk, because your acceleration is getting greater. And then as the trampoline's starting to launch you back up, your acceleration gets less and less and less. When the blue peaks, that's where the red line crosses over to the negatives, and you experience negative jerk as your acceleration is decreasing. This website has even higher orders of a trampoline bounce. The blue line, again, -1 gravity when you're airborne. When you touch the trampoline, you start accelerating until the trampoline stretches out completely, and then you start, you still accelerate, but less until you're back here. So then, what is it? The red line is jerk, where it goes up, then down, and then back. The green line is snap, which it makes like this M. So it kind of makes this S shape around the jerk curve. So it goes up, down, and then levels out. And then the crackle is, wow, that's crazy. Up, down, up, down, up. On a trampoline, you experience higher orders of derivatives of speed. There you go. In conclusion, Matt Parker experienced higher order derivatives of snap and crackle. And yes, I believe While there might be some noise in his data, I believe the spikes for the snap graph are completely accurate, and he could even make a derivative of snap and show the crackle he experienced, the pop he experienced. Matt's a smart guy. He could probably figure out why the units are so big. That's all I got. Yes, you experienced snap.